Welcome back, everyone. I am absolutely thrilled to have you here for another explainer. Today, we're diving into a beast of a topic, machine learning. My goal for this session is pretty straightforward. I want you to walk away with a crystal clear mental model of how machine learning actually works, but without getting totally bogged down in complex calculus or dense code. We're going to build this understanding piece by piece, visually, logically, and systematically. Let's get started.
Okay, let's dive into this. You know, we hear these buzzwords literally everywhere today. AI, machine learning, deep learning. They constantly get thrown around interchangeably in headlines and marketing. But do they actually mean the same thing? Like, is every piece of software we interact with today artificial intelligence? Well, before we can even begin to understand how a machine learns, we really need to define the environment it operates in.
So here's our game plan for today's explainer. 1. The universe of AI. 2. Supervised versus unsupervised learning. 3. Drawing the best line. 4. Classification and squashing lines. 5. Overfitting and regularization. And finally, 6. Measuring success and accuracy.
Starting with Section 1, the universe of AI, let's zoom all the way out.
To get the macro view here, think of these three terms like Russian nesting dolls. The biggest, outermost doll is artificial intelligence. AI is really just the process of creating applications that perform tasks without human intervention. When Netflix recommends an action movie because you've been on an action movie kick, or a Tesla navigates a highway, that's AI. Now, pop that doll open, and inside you find machine learning. ML is a subset of AI. It gives us the statistical tools and mathematical equations to analyze data and make predictions. And finally, the innermost doll is deep learning. This is a very specific subset of ML that uses multi-layered neural networks to literally mimic how the human brain learns to solve incredibly complex problems. But today, we're really going to be focusing on that middle doll, machine learning. Moving on to Section 2, supervised versus unsupervised learning. So how exactly do we use statistical tools to make a machine learn from a bunch of data? Well, we categorize this into two major learning styles, supervised and unsupervised learning. The whole distinction here is about the presence of an output, what data scientists call a dependent feature. In supervised learning, you feed the machine data that already has the answers. So if you want to predict someone's weight, you train the model with hundreds of examples of people's ages and their actual weights. The machine has a very clear target to aim for. Unsupervised learning, on the other hand, is entirely different. There's no output variable, no target. Imagine just giving a machine data on customer ages and salaries and basically asking it to find patterns. It groups or clusters people into similar segments, like finding a group of young, high earners so a marketing team can target them. So it's really grouping versus predicting.
Section 3, drawing the best line.
Let's zoom in on supervised learning and tackle a really foundational concept called linear regression. What's absolutely fascinating here is how simple the core goal actually is. If we plot our data points on a graph, say age on the bottom axis and weight on the side, linear regression is literally just the process of drawing a straight line right through them. But it can't be just any line. It has to be the best fit line. The perfect line is the one where the distance between the actual real-world data points and the points predicted by our line is as small as theoretically possible. We call this distance the cost, or squared error. But how does a machine systemically find this perfect, lowest cost line without just guessing randomly until the end of time?
Well, it uses this brilliant mathematical process called gradient descent. Think of it like a hiker trying to walk down a mountain to find the absolute lowest valley, which we call the global minima. But they're doing it in the pitch dark. The hiker starts at a totally random point on the mountain. They calculate the slope of the ground beneath their feet. That's our cost function, or squared error. Feeling that the slope goes downward, they take a carefully sized step in that direction. The size of that step is called the learning rate. Now, if the learning rate is way too big, the hiker might completely jump over the valley and land on the opposite mountain. But if it's too small, it's going to take them forever to get to the bottom. With just the right step size, though, they continuously update their position until the ground levels out completely. They've reached the global minima, which means they've found the exact parameters for the ultimate best fit line.
Which brings us to Section 4. Classification and squashing lines.
But wait a second. Predicting a continuous number like a person's weight is great, but what if we're predicting a category? Consider this. You want to predict if a student will pass or fail an exam based on the hours they studied. Let's say pass is a 1, fail is a 0. Why can't we just draw our trusty straight linear regression line through this data? Well, a straight line goes on forever. What if a student studies for an insane amount of time, a total outlier? That one extreme data point will pull the straight line completely out of whack. Suddenly, a student who studied enough to easily pass might be predicted to fail, just because the line tilted to accommodate that one outlier. Plus, a straight line will give us weird, nonsensical predictions like 1.5 or negative numbers, which makes zero sense for a binary pass or fail.
And this brilliantly illustrates why we need logistic regression. To fix the outlier problem, we take that straight line and we pass it through what's called a sigmoid activation function. This mathematical tool literally squashes the straight line into this really elegant S-curve. Suddenly, no matter how extreme the outliers are, the output is strictly contained between 0 and 1. It solves our outlier vulnerability instantly, and it allows us to read our predictions as clean, easy-to-understand probabilities, like a 0.8 chance the student will pass.
Section 5. Overfitting and regularization. Okay, so our machine is learning. It's drawing lines. It's squashing curves. But now we face a massive pitfall. What happens if the machine learns the data a little too well? This introduces the very real danger of overfitting. Imagine you have a few data points, and your machine gets incredibly lazy, or maybe just paranoid, and decides to draw this highly complex, squiggly line that perfectly connects every single dot. On paper, your cost function is 0. It looks perfect. We call this low bias because it memorized the training data flawlessly. But the moment you introduce brand new, unseen test data from the real world, the points land nowhere near that squiggly line. It fails miserably. We call that high variance. The machine didn't actually learn the general trend at all. It just memorized the dots. And to fix this, we need some mathematical safeguards.
We prevent this whole dot-connecting disaster by using regularization, specifically ridge and lasso. Think of these as penalties we add to the machine's cost function so it doesn't make the line too steep or overly complex. Ridge, or L2 regularization, adds a penalty based on the square of the slope. It pulls the line back, reducing its steepness to create a smooth, generalized model rather than a crazy, squiggly one. Lasso, or L1 regularization, uses an absolute value penalty. But Lasso actually has this incredible superpower. If you feed the machine a completely useless piece of data, like trying to predict a house's price based on the gender of the buyer, Lasso will actually shrink the mathematical weight of that useless feature all the way down to 0. It acts as a built-in filter, eliminating irrelevant variables entirely while preventing overfitting. It's amazing. And finally, Section 6, Measuring Success and Accuracy.
So we've built our model. We've smoothed out the lines. Now for the ultimate test. How do we definitively evaluate if our model is actually intelligent? Now, you might be thinking, just look at the accuracy percentage. But accuracy can be dangerously misleading, especially with imbalanced data. Let's say a dataset has 900 negative outcomes and 100 positive ones. A completely dumb machine could just guess negative every single time and score 90% accuracy. Instead, we use something called a confusion matrix. This grid breaks every prediction down into 4 realities: true positives and true negatives, where the machine was right, and false positives and false negatives, where the machine was wrong. Breaking our errors down exactly like this is absolutely critical. So, the crucial point here is that not all errors are created equal. Depending on the real-world problem we're trying to solve, one type of error can be a minor annoyance, while the other can literally be catastrophic. This brings us to the ultimate trade-off between two metrics: precision and recall. Let's look at a spam email filter. If an email goes to spam when it's actually an important message from your boss, yeah, that's a false positive. It's highly disruptive, for sure. Here, we want high precision, meaning out of all the emails the machine labeled as spam, we want to be absolutely sure they are truly spam. We are prioritizing a reduction in false positives. But now, look at predicting cancer. If a patient actually has cancer, but the machine predicts they don't, that's a false negative. That is deadly. In this scenario, we don't care nearly as much about false positives. If the machine triggers a false alarm, the doctor just runs more tests. But we absolutely cannot afford a false negative, so we optimize for recall, focusing entirely on finding every single actual positive case. And that brings us to what I think is the most vital lesson of machine learning. The math gives us the tools to draw the lines, to squash the curves, and to filter out the noise. But the machine doesn't know the context of the real world. When we celebrate a model being 90% accurate, we have to look very, very closely at that confusion matrix and ask ourselves who exactly pays the price for that other 10%. Is it just an annoyed email user, or is it a patient losing critical treatment time? Understanding machine learning isn't just about understanding algorithms, it's about making wise, human choices about how those algorithms handle failure. I highly encourage you to keep exploring these trade-offs as you notice AI popping up more and more in your daily life. Thank you so much for learning with me today, and I'll see you in the next explainer.